Degree of vacuum necessary to achieve thermal insulation. Consider a cylindrical dewar of the usual double-walled construction. The outer diameter of the inner wall is 10 centimeters. The inner wall has a 10 centimeter diameter. The inner diameter of the outer wall is 10.6 centimeters. So this is 10.6. Therefore, this would be 5.3 centimeters radius. So the space in between is 0.3 centimeters. That's delta R. The dewar contains a mixture of ice and water. The outside of the dewar is at room temperature. So inside is ice and water, therefore it's 0 degrees Celsius. Outside is room temperature kept at 25 degrees Celsius. Part A. If the space between the walls of the dewar contains helium gas at atmospheric pressure, calculate approximately the heat influx in watts per centimeter height of the dewar due to heat conduction by the gas. There will be heat flux from the outside to the inner portion of the dewar. A reasonable estimate for the radius of a helium atom is about 10 to minus 8 centimeters. So thermal conduction due to helium gas, therefore we need to know the thermal conductivity of helium, which according to our elementary kinetic theory is given by 1 over 3 n V bar Cl. The number per volume, number density, mean speed of the molecules, the heat capacity per molecule, C and L is the mean free path, and therefore we can say that the heat capacity per molecule is the derivative of the mean energy of a molecule, del epsilon bar, del T with respect to temperature. The mean speed of the molecules in this theory we estimate to be equal to the RMS speed, which is 3 kT over m square root, 3 times thermal energy divided by the mass of one molecule. Now, what is the mean energy of a single molecule? It's 3 over 2 kT due to equipartition theorem. It's a monatomic gas, and we have the heat capacity per molecule 3 over 2K, derivative with respect to temperature. That's because we have only translational degrees of freedom. So 1 half mvx square, 1 half mvy square, 1 half mvz square, which gives us this 3 over 2 kT due to equipartition theorem. The total scattering cross-section sigma is 4 pi r square, where r is the radius of a helium atom. The radius of a helium atom is about 10 to minus 8 centimeters. So r is 10 to minus 8 centimeters. Therefore, we can calculate the total scattering cross-section to be 4 pi 10 to minus 16 centimeters square, which is 4 pi 10 to minus 20 meters square. Okay, so if we substitute to our thermal conductivity, kappa helium is 1 over 3 and V bar C. For the mean free path, we use 1 over square root 2 n sigma, number density times the total scattering cross-section. The n's cancel, and therefore we have V bar C divided by 3 square root 2 times sigma. And for this, we can substitute square root 3 kT over m for the V bar. So let's do that here. V bar is estimated to be 3 kT over m square root. C is 3 over 2 k, Boltzmann constant. Then we have 3 square root 2 sigma at the bottom. And then we will have the 3's canceling here. And we will be left with square root of 3 over 8. 3 over 8. K goes inside as k squared, so we obtain k cube t over m in square root, and then we have 1 over sigma, total scattering cross section. Now, what is the mass of one helium atom? It is the atomic weight 4 grams divided by Avogadro's number 6.02 times 10 to minus 23, and converted to kilograms it's 4 10 to minus 3 kilograms. And for Boltzmann constant we have 1.38 times 10 to minus 23 meter square kilogram second to minus 2 Kelvin to minus 1. So if we substitute these values for the thermal conductivity of helium, we find 3 over 8 square root. Now I have Boltzmann constant 1.38 times 10 to minus 23 cube. Temperature is approximately 300 Kelvin. Then I have this divided by the mass of one atom, that is Avogadro's number 6.02 10 to plus 23, 10 to 23, divided by 4 times 10 to minus 3 square root, and this multiplied by 1 over sigma 4 pi 10 to minus 20 meter square. So if you calculate this, we obtain for the thermal conductivity 0.053 watts per meter Kelvin. Now, as for the heat flux, radial heat flux, we have the law of thermal conduction minus thermal conductivity del T del R, the gradient of temperature. So this is the power heat conduction per second divided by the cross-sectional area, which is 2 pi RL. Now, since the heat is flowing inward, we need to consider the surface area of the cylinder, which is 2 pi R times L. So this is going to be 2 pi R times L. That's the area. So this will be equal to, it of course depends on where we are. So it's going to be P over 2 pi RL is minus kappa del T del R and we can see that P divided by L will be equal to minus 2 pi R kappa del T del R, and this will give us P over L dr over R multiplied by kappa is equal to minus 2 pi times dt. So we have dt dr. And if we integrate this from r is equal to 5.3 to r is equal to 5, so from r is equal to 5.3 centimeters to r is equal to 5 centimeters. Here we have temperature changing from 25 to 0 degrees Celsius, 25 C to 0 degrees Celsius. We will obtain P over kappa L natural logarithm of 5 over 5.3 is equal to minus 2 pi minus 25, and this will give us P over L is equal to kappa times, so minus 2 pi kappa, which is 0.053 multiplied with minus 25 divided by natural logarithm of 5 divided by 5.3.